Hey, you're listening to Dr. B, and let's talk about significant figures. Have a look at this measurement and tell me how many milliliters we have in that graduated cylinder. The proper answer is 32.0, and that should be very informative. We do look like it's 32. I see that right there, but notice that the zero's there. That's because that measurer right there did what they were supposed to, and they included the known digits, which is clearly 32, plus one estimated digit, which they figure is right on the nose, 32.0. Also, you could write down that you always measure for liquids the bottom of the meniscus. Why it's important to get down to being level with that, I think most people could realize that if you were up there, you might get an artificially high number by missing the bottom of the meniscus. Down here, you might get an artificially low number. And so it prevents what's known as parallax, which is inaccurate readings due to that effect. Some old instruments would put a mirror underneath the value, and that would help minimize parallax, since this would give rise to a reflection unless you're lined up perfectly, in which case it would overlap with the indicator itself, and so it would prevent reflection when it's aligned nicely. Good, so that's measuring, at least for liquids. There are rules for how many numbers to use and which are significant. So let's have a look at them, and let's at least take a stab at why those rules are the way they are. The number 32 is said to have two significant figures because both numbers are clearly significant, meaning that this number cannot be written without both of them. A little silly, I understand, but non-zero numbers are always significant. However, here I could say 3.23 times 10 to the minus 2, so I'm always going to drop leading zeros. Or to put it another way, leading zeros are never significant. How about sandwich zeros? Cannot be written without them. Therefore, this has four significant figures, and sandwich zeros you always keep. Trailing zeros is an if kind of rule. This number might have been counted by 3 sets of 100, and therefore it's not that precise. But if there's the decimal place, they tell you that they really got 300, not 301, and they were counting each and every one. Therefore, one significant figure there, 3 there. The rule is trailing zeros are only significant if there's a decimal place. Keep it if there's a decimal place, dump them if there's not. Let's apply it to this number here. We've got some sandwich zeros, which we always keep. We got some non-zero numbers, which we always keep, but we have a trailing zero, which we keep because there's a decimal place, and the answer is 5 significant figures. Let's apply it to this one, and let's talk number by number. That leading zero, always dump them. That sandwich zero, always keep it. Non-zeros, always keep them. Trailing zeros, keep if there's a decimal place, and there is, so we're only dumping the leading zero. This number has 5 significant figures. How do we round properly? Well, let's do an example. We got 2.25, but we want to express it using only 2 significant figures. Since the answer is 2.3, I think you can see what the rule is. If it's 5 or higher, round up. Adding and subtracting have different rules than multiplying and dividing, perhaps because multiplying and dividing, the errors can become far more invasive as they are multiplied compared to simply added. Okay, so 4.16 plus 3.3, we're adding that. The raw number would be 7.46, but the rule leads us to conclude this is 7.5, which tells us we only keep the fewest number of decimal places when you're adding or subtracting. Almost all students simply memorize that rule. But if you're multiplying or dividing, we keep the fewest number of significant figures. I hope I said that right. Decimal places for multiplying and subtracting. Significant figures for multiplying and dividing. I see 3 for each, so I'm going to record not 2, but 2.00, since each one has 3 significant figures. Some numbers have infinite significant figures, and those would be simple small numbers that are counted. If somebody said they counted 12 cows, that's exactly 12 cows, or 3 oranges. Also exact relationships. 12 inches is exactly a foot. That 1 has infinite significant figures, as does that 12. Sometimes you might observe that you're doing a calculation and it's lengthy enough that you write down some intermediate numbers. Should you write down all 17 that are in your calculator? Well, no. You should, well, I mean, what you should do is only round at the end. So either take advantage of memory values in your calculator or write down plenty. Now, if you're really wondering what the precise answer there is, should you always use as many as you can? No, you won't get a significant answer as long as you carry along an extra guard digit. So if you know the answer is going to be to 3 significant figures, use 4 in your intermediate values or more, and almost all students get nervous about it and they use a ton. Finally, and this is a hard thing to look up, you never find this in a textbook, what about simple combinations? So often when you're doing a calculation, it involves both multiplying as well as, say, adding. How do you do that? Well, here's how you do it. Get the raw number and then apply the more stringent rule. In other words, check out each rule and go with the one that limits more, right? Here's a good example. Taking a number and in parentheses, this should be what we do first. You add those together. The precision will require us to keep 2 decimal places, agreed, because we're adding. We then take that number and with as much precision as we can, we multiply it by 33 and we get a raw number, which is 268.653. Now, let's see what that would be using 2 decimal places. We'd only drop the 3. But using the 2 significant figures, which we must when we're multiplying, changes it enormously. We can't even use 268. We have to use 270 without the decimal place, or 2.7 times 10 to the first. So that's the more stringent application. That's what we got to use. That's what limits the precision, so it makes sense to me. And the answer would be 270, or 2.7 times 10 to the 1. That is significant figures.